We present DynaGuide, a way of steering diffusion policies with active dynamic guidance. Consider this robot policy trained to pick up coffee cups. If there are multiple cups on the table, it will typically pick up the closer one. But let's say we wanted the red cup. This is where DynaGuide comes in. By working with the base policy, DynaGuide is able to steer the robot towards the red cup. This behavior steering is possible without touching the weights of the base policy or requiring goal conditioning. So, how do we do this? Normally, diffusion policies predict the denoising steps to create an action. In DynaGuide, we add a guidance gradient to this process. This changes the action output without changing the pre-trained policy. But how do we get this guidance gradient? We can encode our steering objectives into a set of guidance conditions, which contain observations of desired outcomes and potentially undesired outcomes. We want to change the robot's actions to seek desired outcomes and avoid undesired outcomes. Steering towards a future outcome requires knowing how current actions impact future observations, which is a good fit for a dynamics model. A dynamics model could predict a future observation directly, but comparing the predicted outcome to a guidance condition is difficult in pixel space. So instead, we use a latent dynamics model that predicts outcomes in a latent space from a pre-trained visual encoder. We can project the desired and undesired guidance conditions into the same latent space. This allows us to use simple Euclidean distance to compute the similarity between the predicted outcome and the guidance conditions. All components of the setup are differentiable, which means that we can backpropagate these latent distances through the dynamics model and onto the proposed actions. This gets us a guidance gradient signal. Putting this all together, we use the dynamics model to create the guidance gradient, which we use to influence the action generation. This combined dynamics modeling and diffusion guidance is our DynaGuide method. For more details, refer to our paper submission. Intuitively, DynaGuide seeks the mode of the policy that best satisfies the guidance conditions. This toy example shows how DynaGuide is able to steer a color-agnostic square navigation policy towards blue squares on a variety of scenarios. To understand what DynaGuide can do, we start by conducting a set of experiments using the environment and data from the Kelvin benchmark. First, we are interested in the steering abilities of DynaGuide against relevant baselines. Second, we are interested in the robustness of DynaGuide to lower quality guidance conditions. Third, we are interested in how DynaGuide behaves when the guidance conditions become more complicated. Lastly, we test if DynaGuide can enhance behaviors that are underrepresented in the base policy. We conduct experiments in this Kelvin environment, which contains articulated parts and randomly arranged blocks. It comes with an extensive set of human-collected play data that we use to train a base diffusion policy and a dynamics model. In our first experiments, we look at the ability for DynaGuide to take a diverse policy and narrow its behavior down to one object interaction. As guidance conditions, we only provide positive examples showing successful outcome of that behavior. On the articulated parts, DynaGuide can steer to the target behavior an average of 70% of the time, which outperforms some baselines. But on this very clean setup, the specially trained goal-conditioned baseline performs nearly perfectly. But what happens when the guidance conditions become less clean? We look at another experiment involving randomly arranged cube objects. Guiding the robot to the randomized cubes is a challenge because the guidance conditions depict outcomes that are mismatched from what is currently possible. DynaGuide's expressive latent space allows it to still steer the base policy, and the performance becomes equivalent to the specially trained goal-conditioned model. Inspired by those findings, we look at what happens when the guidance condition decreases further in quality. Previously, the robot's end position helped specify the desired behavior. In this experiment, we use guidance conditions where the robot and all non-target objects are fully randomized. Although DynaGuide decreases in performance, its ability to leverage all the guidance conditions allows it to extract a meaningful steering signal. In contrast, the goal condition policy is out of distribution and performs poorly. In addition to improving robustness to lower quality guidance conditions, DynaGuide latent dynamics also allows guidance towards multiple behaviors and also avoiding undesirable behaviors. As seen here, DynaGuide can indeed steer towards multiple behaviors and avoid behaviors too. On these complex objectives, DynaGuide's active diffusion guidance notably outperforms a passive sampling baseline. DynaGuide's active guidance means that the dynamics model can actively seek behaviors that are more rare in the base policy. In this experiment, we changed the base policy's exposure to one behavior in the training set. As the data decreases in representation, the base policy offers less of that behavior. Sampling approaches boost this behavior, but they are still affected by this underrepresentation. However, DynaGuide's active guidance maintains nearly 40% success rate, even at 1% data representation. We continue by investigating DynaGuide on a real robot setup. First, we are interested if DynaGuide can successfully steer an off-the-shelf policy. Second, we test DynaGuide's ability to seek behaviors that are rare in this policy. Lastly, we test if DynaGuide can steer a base policy towards a behavior that it was never trained on. For the base policy, we use an off-the-shelf policy trained on the Universal Manipulation Interface setup. We train a dynamics model using data collected on the Universal Manipulation Interface, downloaded from public datasets and from our experimental setup. In the first experiment, we give the robot a choice between two different colored cups. We want to see if DynaGuide can create a color preference in the base policy. As guidance conditions, we use trajectories of the desired colored cup. The base policy does not have a color preference. However, DynaGuide can steer the robot to grab the red cup 75% of the time, or grab the gray cup 70% of the time. This shows that DynaGuide can successfully steer this off-the-shelf policy. For our next experiment, we are interested if we can enhance an underrepresented behavior. We place a red cup directly behind a gray cup and try to steer the policy towards the red cup. The base model prefers the closest cup and only grabs the red cup 25% of the time. But DynaGuide shifts this preference and the policy goes past the gray cup and to the red cup 80% of the time. In our final robot experiment, we are interested in steering the base policy to interact with an object it has never seen before. The base policy only arranges cups, but we try to steer it towards a computer mouse. As expected, the base policy avoids this novel object. The dynamics model is trained on data containing computer mice, so it is able to guide the robot towards the computer mouse and double the number of interactions with this foreign object. In conclusion, our method of using external dynamics model for guidance successfully steers policies towards guidance objectives and provides greater guidance robustness than goal conditioning. In addition, DynaGuide can also avoid undesirable behaviors and can be steered towards multiple behaviors. It works on real robot setups and on off-the-shelf diffusion policies. For more details, please refer to our paper. Thank you.